Hello everyone, welcome to Math 251. As mentioned in class, we have this holiday on Monday and we can't afford to miss a day, otherwise we'll be very behind. So what the purpose of this video is to point out the stuff that you should read up before our class on Wednesday. So ideally, you should be enjoying a long weekend, but you will be back to school on Tuesday. The Tuesday recitations would not have questions on what we're going to talk about in this video, so you'll be fine. So you have the entire Tuesday all the way to Wednesday till evenings to catch up on this particular material, which I will assume on Wednesday that you have already covered. Okay, so we are going to continue to use our lecture notes to go through some of these examples because this is easier for me. Easier for you too because you have all those notes, so you just kind of like have to look at the example on the notes and then kind of like let me basically point out the important idea behind it and quickly guide you through the material that we're supposed to be covered on Monday. All right, so we were talking about equation of line and equation on plane, right? So this is section 12.5. There's some problem, hang on. All right, I think I solved the technical problem, so let's get back to what we're doing here. So section 12.5, we are looking at equation of lines and equation of planes. So very quickly, the equation of planes, in order to set up the equation of planes, we would need to have one point that's on the plane and the normal vector that is a vector that's normal to the plane. Once we have that, we would know how to get the answers for that equation of the plane. For equation of the line, we need one point that is on the line, and we want a directional vector. We want a vector that's parallel to the line. So on Wednesday, right? Yes, on Wednesday, the very last example that we talked about is we were looking at what happens when we have two planes, right? They are intersecting each other, right? So we have this plane here, two planes here. They are intersecting each other. And then we already know how to figure out this angle here, okay? So we already know how to figure out this angle here. So now the next questions that we would like to talk about is that since they intersect each other, so the intersections, the places where they intersect actually will form, there will be a line. That line is going to be the line of intersection between that two planes. So the question now is, how are we going to find the equation of this line? So again, every time when there are questions about line, you will have to think about, number one, can I find a point that's on the line? Well, since there are infinitely many points on the line, you should be able to find one. And then we will need to find a vector that is that is parallel to that line. Okay, so there are two things. Let me write it down. Okay, number one, we need to have a point that's on the line. So a point, okay, on the line. And then we would like to have number two, a vector, right? A vector that is parallel, right? Parallel to the line. All right, and if you remember, we have this equation here that I call it x plus y plus z equals to 1. By the way, in the actual homework or exam, you do not really have to know how that plane looks like, okay? So this is, I mean, I don't know how this plane looks like that. Okay, I am just basically construct a conceptual pictures just for the understanding of it, not for the precisions of it. So some of you, I saw that you are using apps that is available online to try to sketch, try to plot out all this plane. It doesn't really help so much. Sometimes the situation is even worse because it's very complicated and it doesn't really help. So you want to create a clean conceptual picture. So I would say this is a clean conceptual pictures that we have, right? Okay, so all right, so now I need to find a point that's on the line. So in this example, it is easy to see the point, for example, the point, okay, 1, 0, 0 is on the line. Now, how do we know that? Well, because 1, 0, 0, look at this, 1, 0, 0, right? Solve this equations, solve this plane equation. That means that 1, 0, 0 is on this plane, and 1, 0, 0 is also on this plane right here. So 1, 0, 0 is common on both planes, so they will fall into the line, the intersecting line, right? So we now know, okay, 1, 0, 0 is on the line, okay? So that's one of it. So 1, 0, 0 is on the line. Now, some of you might object and it's like, how would I know in general? What happens when the equations are too complicated? Well, yeah, it's not, we can still solve it. We can actually find all the answers. Actually, we can actually find all the answers that's on the line. There's another way of solving this problem. It's involving techniques in linear algebra. But in order to do this particular method in Math 251, I will try to give you something where the point of intersection is easy to see. So we don't have to worry too much how to actually find the point of intersection. So in this example, for example, you look at this and you will know that 1, 0, 0 is on the line. You can see it pretty easily. So what happens to the vector that's parallel to the line? How do we find that? Well, the idea is actually pretty straightforward as well, because remember that we change our point of view and look at the things like this. So imagine that you're putting your eyes over here and look at it that direction, right? So if you look at it from here, you will have this plane right here, this plane right here, that's the angle theta. So we know that we have a normal vectors, okay, to this plane. We have another normal vector to this plane. You remember, the vectors can be moved as long as they point in the same directions and have the same lengths as the same vector anyway. So instead of writing it like this, I'm going to just move all this two of this vector. One of it, I'm going to move it here. And then another one, I am going to move it here. And then imagine that, let's say this is normal vector number 1, this is normal vector number 2. And you see that when you when you cross these two vectors, then you will have a vectors coming out to the plane, right? You have a vectors that is coming out to on the screen. If you look at it like that, there will be a vector either pointing out towards you or pointing at the back of your computer monitor, right? So that vectors, which is n1 cross n2, right? n1 cross n2. If you look back to this picture, okay, take this point of view again, you'll see that n1 cross n2 is going to be a vector that is either in this direction or in the opposite direction. And that directional vector is the vectors that is parallel to the line, okay? So this brings back to another very important question here, is that, okay, I know what I need to do to find the directional vector, which is take the cross product of the normal vectors, but how would I know the normal vector of that two plane? And we also mentioned that before, the normal vectors of that two planes can be very easily identified just by looking at the coefficients. So this is coefficient 1, this is coefficient 1, this is coefficient 1. So this, if you call this normal vector 1, the normal vector 1 is going to be, that's terrible color, it's going to be 1, 1, 1. Okay, don't get confused with too many things over here. And then this second normal vectors, right, that's on here, look at the coefficients of the plane that describing that particular plane, the plane equation that describe that plane. Look at the coefficient again. Let's call this n2. N2 is this one here. So n2 here is going to be 1, -2, 3. So this is going to be a vector that's normal to your second plane, which is the horizontal one in this picture. Okay, call it first plane, the second plane. And once you know that, everything will be very easy, because taking the cross product, as you can see here, taking the cross product will give you the directional vector. So the directional vector, okay, so the directional vector turns out to be 5, -2, -3. Refer to your notes, or you can just do it yourself. You'll see that. So this is a directional vector. And then what is one of the point that's on the line? This is a point that's on the line. So because of that, immediately we can write the vector form of our line equation is 1, 0, 0 plus t, and then 5, -2, -3. Once we know that, we can write in whatever form that they want. So they want a parametric form, or they want to have symmetric form, or whatever. It doesn't really matter, because once we see this, immediately we know our x is equal to 1 plus 5t, our y is equal to -2t, our z is equal to -3t. Okay, that's a parametric form. Okay, so that kind of concludes that example that we saw on Wednesday. Now we would like to talk about another concept here. I think we can continue here. I'll try to make the videos in different parts. So let's look at one more example before we move to another videos. And I want to make the videos too long, so I'm going to cut it into sections. All right, so the next questions that we have is the following. So the questions is that, let's look at this problem here. Let me go to another page. We'll be back. Hang on a second. All right, let me go to another page here. Okay, so the second things that we want to talk about is the following. So suppose you have a plane, okay? So you have a plane, and let's say we know the plane equations. Let's say the plane equation is, I don't know, it doesn't really matter, 5x plus y, okay, minus z equals to 1. All right. Again, I don't really know how that plane looks like. I'm drawing a conceptual picture, right? Some of you get confused and ask me, like, how do you know the plane looks like that? You know, it can look however it is. I can change my perspective and put it horizontal because it's easier. I don't want to look at everything slanted. It's difficult to interpret. Okay, can you tell me one of the point that is not on the line? This time, sorry, not on the plane. I want to find a point that is not on the plane. So for example, let's say, let's say 1, 0, 0. Okay, that's the easiest one. Let's say 1, 0, 0. If you put 1, 0, 0 into here, that means take x equal to 1, y equal to 0, z equal to 0, right? So you will have this plus this minus this. That's definitely not equal to 1. So 1, 0, 0 is definitely not, okay, not on the plane. Again, I don't know where exactly it is. I am just drawing this as a conceptual picture, okay. Now, let me get this back. I want this equation. I don't want to delete everything. Okay, now tell me also another point that you can see that is easy, that is on the plane, okay? So there are many, right? There are infinitely many points on the plane. So maybe I can say, I don't know, let's say 1, okay, 0, and 4. Okay, 1, 0, 4 is on the plane. Let's double check that. 5 times 1, right? Plus 0 minus 4, is it equal to 1? 5 minus 4 is equal to 1. So, yep, so 1, 0, 4 is, okay, let me draw it here. So I don't know it's directly below it, right? I don't want you to get the wrong concept. So 1, 0, 4 is on the plane. 1, 0, 4 is definitely on the plane. 1, 0, 0 is not on the plane. Okay, cool. What do we want? What do we want to do? Well, what I want is that, let's say we look at this, okay? Look at this is our point here. And then I wanted to know what is the shortest distance from this point to this plane. Obviously, that means that this has to be 90 degrees, okay? Because if it's not 90 degrees, this distance here, for example, that's not height. It's not the shortest distance, right? That is longer. That is also longer, for example. So the shortest distance between the point and the plane is the one that is directly below it, so to speak, right? Okay, and it is 90 degrees. God, it's 90 degrees to that plane. Okay, so the objective is to find this distance, all right? So this distance here, okay, so this distance here, that's our distance D. This is our shortest distance. Now, again, there are many different ways to solve these problems. You can use Calc 1 and look at the distance functions, blah, blah, blah. You can use calculus, take the derivative, maximize the thing, minimize the thing. But we wanted to solve this problem by using some of the stuff that you know already. For example, dot product, right? For example, that kind of stuff to help you answer these questions. So again, this is one way of solving this problem, not the only way. And in order to do that particular kind of problems, I will need a point that's on the plane, which I have that already, okay? So let's call this P, all right? Let's call this Q, right? This is given, okay? All right, this is given. And then I say, what is the distance, all right? What is the distance? Okay, what is the shortest distance? This is given point. What is the shortest distance? So I need, number one, I need to find a point that's on the plane. We know that already. Find any point that's on the plane. Doesn't really matter. There are infinitely many points on the plane. For example, let me give you one more, okay? 1 over 5, 0, 0. That's also on the plane, right? Okay, there are many. All right, so find just one. Just one of them. And then I want to construct this vector here. Okay, so this vector here is called PQ, right? So that's our vector here. This is our vector PQ. Okay, so this is our vector PQ. All right, let's change color. Let's say this is our vector PQ. All right, so our blue one is our vector PQ. Now, what do we want? We want to also bring up another vector. So another vector that I want to bring it up is our vector, the normal vectors. So let's bring out a normal vectors. So normal vectors to the plane. Again, one of the very important idea is that if you already know the plane equations, look at the coefficients, right? We talked about this before, 5, 1, -1. That's the normal vectors, okay? Again, I don't know the normal vector is actually pointing this way or the opposite direction. Again, this is conceptual picture, so let's do it. Let's put it here. This is our normal vector. All right, now let's call the angle between the normal vectors and the blue line, the PQ. Let's call that theta, okay? Let's call that theta. All right, okay, so now, if you look at this triangle, okay? So if you look at this triangle, all right, let's look at that triangle. So if you look at that triangle, okay, let me redraw it here. All right, so I am drawing this triangle here. So I'm drawing a triangle like this, okay? This will be the distance in terms of the length, okay? The normal vectors, okay, don't get me wrong, the normal vector might not be that long, okay? It doesn't matter. The normal vector maybe is just like that, okay? It's not all the way up to there to form a triangle. No. I'm saying that if you translate this D to the other side, right, and then form a triangle. So you have a D like that. You have a vector PQ. That's your P, that's your Q. So you have a vector PQ, which is right here. So the length of this triangle on the hypotenuse is going to be the magnitude of PQ. And then we say we have this theta, so we have this theta. All right, so now high school trick, preschool trick. I don't know when you learned this, but now if you take cosine theta, right? If you take cosine theta based on this triangle is extracted from our picture over here, right? Okay. Now, cosine theta is going to be D over the hypotenuse PQ. So D will be PQ, okay, cosine theta. Okay, so our answer is PQ cosine theta. Now, what do we know? We know P, we know Q, so we know vector PQ. We know vector PQ easily. Let's do that. So that will be 1 minus 1, right? 0 minus 0. And then 0 minus 4, right? Take the Q, right? Okay, and then minus that. Okay, let me write that again. So our vector PQ is 1 minus 1, that's 0. 0 minus 0, that's 0. And then 0 minus 4. So that is going to be -4. So I know vector PQ. So I do know the length. All right, so in order to find the shortest distance, I already know this. I just have to figure out this. But this is hard because I don't know what that theta is, right? I created that theta right here, but I don't really know what that angle is. But you know, we also seen something like that before, which is that, all right, let's rewrite this. D is PQ here, all right, cosine theta. But let's say I wanted to bring in an extra term here, which is, okay, let me rewrite this. So this is cosine theta. So I want to bring in an extra term, which is this, the magnitude of the normal vector. I can't just do that. I changed this a thing already, so I have to do this. And again, why do I want to do it like that? Because the numerator, right, is nothing but PQ dot n. And then the denominator is the magnitude of n. Perfect. We have everything now because I do know n though, right? I know PQ. And now I don't have to deal with theta. I can immediately compute this answer here. So the magnitude of the normal vector is going to be 5 squared plus 1 squared plus 1 squared. How do I know? I'm looking at this, okay? That's our normal vector. All right, so right here on the top, PQ is 0, 0, -4, dot. Okay, what is our normal vector? 5, 1, -1, okay? So our dot product, don't care because, you know, it's 0. And then that gives us 4. So that gives us 4 over square root of 25, 26, 27. So 4 over square root of 27 is the answer for that questions that we asked, which is what is the shortest distance between that point and the plane? Okay, you see that? So all right, so okay, let's just hold on for a minute. Let's just look at this whole picture here. I just want to comment a little bit. It is lucky. I mean, I didn't plan this. Okay, but so happened it was lucky that the D here give you a positive number, because all these pictures are drawn conceptually. You don't really actually know the actual orientation of everything. Sometimes you will get a negative number. So if you get a negative number, just drop that negative value, or basically take the absolute value of that, and that will be your distance, because our distance here is not supposed to be negative. Okay? All right, so let me recap this real quick. So suppose, right, you have a plane equation, right? Ax plus by plus cz equals to d. And then you are given a point. All right, you're given a point, x naught, y naught, z naught. This is not on the plane, so you draw it here. X naught, y naught, z naught. This is not on the plane, okay? All right, okay, that's not on the plane. You've been given this, and you also been told it is not on the plane. So what do you want? Shortest distance. All right, so how do I do that? Number one, from this equation, find out one of the point that is from this equation, and then call it PQ if you want. And then construct this, okay? So you have vector PQ, right? And then you have the normal vector, right? So dot the normal vector, right? Divided by the magnitude of the normal vector, that's the distance. If this thing turns out to be negative, take the positive value. So you do that, okay? All right, so that's what we did. Basically utilizes middle school trick and the dot product. So how do we get this, right? How do we get these equations? Shown you already. The reasoning is right there. But procedurally, if you want to have a recipe, you are like, what should I do? What should I do? The recipe is that find a point that is on the plane. You should be able to do that. It's not given. You have to find one. And then from here, you construct this vector PQ. And then you know the normal vectors. You definitely know the normal vectors if this equation is given. Dotted, divided by the magnitude of the normal vector. That's it. That's the distance d. Okay? All right. So that's one more example, and then we switch to another video. So the other example, which is the last example for sections 12.5. Okay? Not the last example, but anyway, it's okay. Let's just look at this particular problem here. Okay, so what they are saying is now the following. Suppose you have a plane, you have another plane, and they are parallel plane. Okay, they are parallel plane. So let's say, let's say that this equation here is 10x plus 2y minus 2z equals to 5. I'm copying this thing here. Again, I'm drawing it conceptually. I don't really know exactly where they are, but the other one is 5x plus y minus z equals to 1, okay? And you should be able to tell that they are parallel, okay? Think about it. Why is it that giving this equation, the plane equation and this plane equation, think about it for a second. Like how do you know that they are parallel? Okay, reason is simple. You look at the normal vectors. Again, we can read the normal vectors from the plane equations. It's 5, 1, negative 1. Look at this normal vector here, okay? Let's call it plane 1, plane 2. Okay. Let's call this plane 1, fancier notation, plane 2. Okay, too many p, so let's use pi, for example. We haven't used pi at all. So this normal vector here for this one, plane 2, again, is 10, 2, negative 2. And you should be able to see their parallel. Why? Because their normal vectors are multiple of each other, right? So their normal vectors are multiple of each other, so they are parallel planes. Because if your planes are not parallel, so let's say this is the normal vectors of this plane, and then you have another plane like that, their normal vector is this one. So this normal vector 1, normal vector 2, they are not multiple of each other because they are not parallel. And you can see the thing is that the plane will not be parallel. So if your plane is parallel, you would know that the normal vectors are multiple of each other. So I hope this is clear. All right. So back to this. So they are parallel, but they are not the same plane. Okay, they are not the same plane because, okay, how do you know they are not the same plane? Well, look at this part here. This is 2 times of this, right? So if they are the same planes, then this should be so this should be 2, right? But this is 5, so they are not the same plane. Okay, so if they're not the same planes, then we can also now ask the following questions. What is the shortest distance between these 2 planes? Okay, what is the shortest distance between these 2 planes? Again, that means that we are looking at the line, which is right, perpendicular to this, perpendicular to that. So that will be the shortest distance. The question now is, how do we find them? This turns out to be a super easy problem if you already know how to do the previous problem, which is a point and a plane. Now you have 2 planes. So I want you to think about it a little bit. If you don't want to, I can also tell you the right answer right away, is that it is the same method because I just need to find a point that's on the plane. Okay, so for example, let's look at one of the points is on this plane. Well, let's try that again. We know 1/5, 0, 0 is on that plane, for example. And then I don't need to look at the plane anymore because I just need to look at this point, right? 1/5, 0, 0. If I can find the distance, shortest distance between this point and this, I get the shortest distance between the 2 planes. So it's very easy. What you need to do is find one of the points that's on the plane and then reduce that problem to the problem that you have seen before. And that's how you do this kind of problem, okay? All right, I am going to leave the last example here for you to read about it because it's not very complicated. The questions in this problem here is that, remember that we talk about when we have, right, we are in R3, so we have more space to move around. And when when you can actually have a line that's like this, another one that is like that, and they are both from different plane. One is this plane, another one is that plane. Like, look at this picture, for example, right? So they don't have to intersect, right? They are not parallel. These are not parallel line. They don't have to intersect because we have enough space. So the question is, for this problem, is the question is that what is the shortest distance between that 2 lines? And if you look at this example, they reduces this problem by looking at what is the plane, right? So the line, the 2 skew line, you can place a plane on one of the line, you can place another plane on one of the line, and then from here you can use the methods that you saw earlier to find that distance. So I will leave that to you. So this is basically done. We are done with 12.5, and we're going to see you in the next videos on the next sections. Okay, all right, thank you, see you there.